field.
These are right on your U of R page, the links?
Yeah, although, yes, they're in my class web pages mostly. I mean, I can send you the link.
Sure, great.
So you can change the charge of the particle to look at the electric field, then you can add in another one and add those fields together. You can look at the fields separately. And so all of this is really nice for talking about the ideas of the fields and vector superposition and those kinds of things. For some reason, flux through a surface is always a bit of a hard one. So, so if we have an electric field and we talk about the idea of flux, and you can change the angle to sort of talk about how the number of field lines that go through the surface vary, and the fact that when they go through the other direction, you get negative flux.
These were all developed by a startup at RIT?
No, it was at the University of Rochester.
Oh,
It's called Truth and Beauty Software,
Yeah.
and basically, you know, I walked in and gave them a dream list, and then we went back and forth. Actually, it was really fun. I had this whole group of programmers basically doing whatever I had to do. I want that to look red. I want this to be bigger. I've never had anything like that in my whole life. I usually just get people looking at me, yeah, we'll go do it. You know? So it was really great. So here I have a particle cannon basically shooting particles into magnetic fields. And you can have a lot of fun with this one, actually. So you can change the strength on the fly and the direction. You can put the field two separate directions. You can make this thing shoot at angles, change the velocity, and the charge of the balls. So there you've got all the various handles that you want to talk about it, and I find that it's a little more fun to do it this way than what I usually end up doing. And I don't know, this is the one where, especially if I've had a beer or something in the evening, and I'm looking to remind myself, like I'll find myself, I'll waste an hour just playing with this. Then magnetic field, so the wire is coming out at you, so you have current going through it. So this is meant to visualize the magnetic field around wires, and it's sort of very similar to the Coulomb that we did. And if you want, you can make the wires go 3D. So
is this public access?
Yeah, these are all these are all public access. Although, admittedly, like I say, you'd have to know where to find them right now. So I mean, I can give you the link. This, for example, is just a page that I have for my class that has my lectures and various things on it. So it's a way you can get there, but it's not. So I find one of the hardest things to put across are electromagnetic waves, and so. So here I can show the electric and magnetic fields as they pass through a plane and propagate. It's a little deceptive because students start to think electromagnetic waves are little packets as opposed to, we're talking about plane waves there. So trying to picture this and give them the feeling that it's in fact an entire plane is always a bit tough. But this is fun. You can change where this is. You can change the wave frequency, make it go fast or slow. You can stop it and talk about it if you want. So I find that one is a time saver because it's really hard to do all this board. And here's a similar one, except now we're actually using the two orthogonal polarization states of an electromagnetic wave, a general one. So basically, if I have a general wave, I can describe it in terms of two orthogonal states where the electric field vectors are at right angles to one another. And if I now look at the superposition of the electric field vectors, then you're talking about polarization. And so here is one that I use to illustrate polarization of different sorts for electric waves. And so in this case, if you imagine that the plane wave is coming through with the two orthogonal states, and I have the two electric field vectors, wow, this takes some getting used to in this classroom. So if you're looking at it on the eye, you see the two electric field vectors of the different colors as they pass through this plane, and then the purple is the vector superposition, which is what you would actually see as the electric field vector for this particular plane wave. And as the plane wave propagates through, you can see this thing is moving in a line, so it's linear polarization. And now, if I offset the angle of one of those orthogonal solutions of that plane wave by, say, 90 degrees, then you can see that they go out of phase, and you can look and see the superposition now moves in a circle. And you can turn on the thing called trace path, so you can see that this is what we mean when we talk about circular polarization, for example. And I guess probably you're not doing this in your classes, but I find when I do, it's really hard. And if you've got a student that's really interested in optics, this is sort of a fun thing to do. In fact, I sometimes am wondering whether I should be doing this in my classes. But the chemists, in fact, when I teach the pre-meds, I mean, they actually use polarization as one of their primary diagnostics, and yet, they don't know what it means when you're talking about putting in phase plates and half-wave plates to change something from circular to linear polarization. But this is another fun one where I can spend hours playing with this. Anyway, so I'll send you a link.
Thanks.
I mean, it would be nice to maybe put a link to these on a wiki, because you may find some of